Hello everyone, we are Junhyeok and Jo. Today we present our project on graphs and sequences of convex sets for minimum time motion planning. Our motivation is reliable minimum time motion planning. We use optimization-based planning because it allows us to generate trajectories that satisfy kinematic and dynamic constraints. GCS helps by decomposing complex and non-complex spaces into a graph of convex sets that preserve global connectivity. And we focus on minimum time objectives because they are both challenging and closely relevant for high-throughput robotic systems in industry. However, GCS alone is not sufficient for acceleration-limited minimum time motion planning, since it can only enforce continuity and velocity constraints, not acceleration constraints. To address this limitation, we introduced SCS. Once we have a feasible sequence of convex sets from GCS trajectory optimization, the question becomes how to turn the sequence into a minimum time trajectory while satisfying acceleration limits. SCS operates directly on this fixed sequence. It searches for a new spatial and temporal profile while enforcing both velocity and acceleration limits. The key idea is that the problem becomes biconvex when we separate it into two steps. First, fixing the transition points and optimizing the transition velocities, and then fixing the velocities and optimizing the transition points. By alternating these two convex subproblems, SCS converges to a minimum time trajectory along the chosen sequence. The problem we aim to solve is the following. We want to find the trajectory qt and the duration t that achieve the minimum time motion while satisfying those constraints. To address this, we break it into three subproblems. In the first subproblem, we simply use iris to decompose the free space into convex regions. In the second subproblem, we run GCSTO using the graph from iris. The key difference is that we do not take the single best solution. Instead, we extract the top k feasible paths, which SS then refines to minimum time. Here is an example of a trajectory produced by GCSTO. While the trajectory satisfies velocity limit, it violates the acceleration limit as shown in the bottom plot. This is why we at the final SCS stage, which explicitly enforces velocity and acceleration limits and aims for a minimum time trajectory.
For our environment design, we desired to create an environment which admits two topologically distinct paths. Difficulties we encountered include achieving sufficient connectivity in the graph of convex sets, as well as handling a continuous revolute joint at the base of the manipulator. We overcame these difficulties by experimenting with different variants of iris and reconfiguring the objects in our environment. The final environment we converged on had one KUKA-IWA manipulator placed in between two shelves. Additionally, we had a short wall on each side and a ceiling which is not shown for ease of visualization. The corresponding graph of convex sets for this environment is shown on the right. Extracting the top 5 probabilistic paths from the GCS solution gives us sequences of convex sets which traverse both clockwise or above and counterclockwise or below our manipulator. A visualization of the most distinct of the 5 sequences is shown here. Quantitatively analyzing the trajectories of each joint, we can see that while the GCS solution satisfies the velocity constraints, the acceleration limits get violated. To generate a baseline with feasible acceleration, we employed TOPRA to reparameterize the time profile of the geometric path obtained by GCS. This provided feasible acceleration while also being minimum time for the given geometric path. However, this new path resulted in a nearly 30% increase in trajectory duration. This raises the question, can the flexibility of SCS consisting of both temporal and spatial degrees of freedom enable a faster trajectory while still satisfying constraints on acceleration? We now turn to the key results of our work. Employing the biconvex SCS motion planning method on each of the top 5 sequences from the GCS solution produces trajectories which now satisfy both velocity and acceleration constraints, as in the case with TOPRA. How about the trajectory duration? The freedom within the biconvex SCS motion planning framework enables us to find a trajectory which is almost 10% faster than the baseline while still satisfying acceleration constraints. This is largely possible due to the ability of SCS to reconfigure the knot points which are used to traverse the sequence of convex sets. Here we can see a rollout of the hybrid GCS-SCS motion planning pipeline against our baseline. The SCS trajectories are characterized by less joint movement and overall shorter duration in each case. In conclusion, in this work, we demonstrated a hybrid motion planning approach combining the established GCS method for high-level decision-making and the recently published biconvex SCS method for low-level trajectory refinement. We showed that GCS and SCS can be viewed as complementary methods, each addressing different aspects of the trajectory optimization problem. We showed that our approach can outperform a comparable optimization-based pipeline, highlighting the potential of this hybrid approach for efficient trajectory optimization in robotic manipulation.